Hey, North Mr. Eagle here. Let's talk about entropy. Entropy is one of the more confusing, hard to wrap your head around kind of concepts in thermodynamics and in thermochemistry, but we're going to try and keep it pretty straightforward and simple as best we can. We have to first start by talking about spontaneity. A spontaneous process is one that happens on its own. So it doesn't need any input of energy in order for it to happen. So examples might include ice melting at room temperature. That's just going to happen on its own, right? Or your phone's battery becoming less and less charged, running out of battery. That happens on its own. The battery never charges itself, right? And so that would be a non-spontaneous. That doesn't necessarily mean that the reaction is fast, right? Don't confuse kinetics with spontaneous reaction. Spontaneous just means that it will occur on its own. We often think of the word spontaneous as thinking of like happening quickly, but that's not what we're talking about in this case. And for that reason, we prefer the term thermodynamically favorable. It's a mouthful, it takes much longer to write, but it's a much better term, and we'll probably use that as much as we can. This relates to the second law of thermodynamics, which says that entropy for the whole universe as a whole is always increasing. The amount of entropy being the dispersal of matter and energy, right? Energy is always goes from high concentration to low concentration, you could say. Now, irreversible, let's go back to that for a second. If we think of this situation where we have two containers, one empty and one full of gas, and they're connected by a valve, if you open that valve, it spontaneously fills the other container, right? It would never fill the molecules once they're separate in the two separate containers would never on their own go back into the original container, creating a vacuum on the other side, right? That would be non-spontaneous. It never happens. Now, so what is this entropy that we're talking about? Entropy is thought of in a couple different ways. A lot of times people think of it in terms of randomness. Sometimes people use the term disorder to refer to entropy. This is the one that I kind of am used to the most, but dispersal is maybe a better term that we'll use. The dispersal of energy and the dispersal of matter is an increase in entropy. Like enthalpy, it's always measured as a change, so you'll see a lot of delta S's. S meaning entropy, so change in entropy. So a change in entropy, an increase in entropy, would be a positive delta S because our final entropy would be greater than our initial entropy. And this can involve the dispersal of either matter or energy, and we'll talk about each of those. Another way to think about it that kind of conceptually helps you wrap your head around it and what's really going on at the atomic level is to think of it as a probability of possibilities. That's a confusing term. Basically, what possibilities are the most likely to occur? Sometimes these possibilities are referred to as microstates. There's a great website that kind of walks you through this, and it uses the analogy of sheep, and it's worth going to. It's a little bit long, but it will really help you understand what entropy is. I'm actually going to go to it and show you just a piece of it. Let's say you have two objects. One starts off cold and one starts off hot. These purple circles we'll use to represent energy, right? If the two objects come in contact with each other, then they start transferring energy, and so you would have purple circles moving down into the colder object, right? But why does that happen? I mean, the cold object, even though we're not showing it, does have some energy. Why does energy not transfer into the hotter object? Why does it always go from hot to cold? Or in biology, why do concentration gradients never go from low concentration to high concentration, but rather from high concentration to low concentration? The reason is because of entropy. And we're going to use a sheep analogy to kind of make sense of this. So let's picture these two objects not as objects, but as fields in which we have 6 sheep. And so the sheep are going to represent energy. If we build a bridge that connects these two fields, the sheep can freely move around, and eventually some will end up at the bottom field. We're going to keep track of how many are at the top field for every microstate. Basically, we're going to keep track of the number of possibilities and which possibility has the greatest probability. Let's go ahead and release the sheep. So here we have, initially, they're just moving around randomly. We have often 4 in the top farm, but once we speed this up and we get more samples, you'd want to have a lot of samples. Eventually, it kind of emerges that it's more likely that you're going to have somewhere in the middle number of sheep on the farm. And I'm going to get even more data. Eventually, 3 becomes the most likely possibility. Imagine rolling a dice. You're more likely to get 7 if you're rolling 2 dice, because there's more possibilities of getting 7. There's only one possibility of getting 12, right? 6 and 6. But there's multiple possibilities of getting 7. And so you're more likely to get 7, just like you're more likely to get 3 here. Let's think about this another way. What if we have two containers of gas? One is at a higher temperature and one is at a lower temperature. And they have a boundary between them, but they can transfer energy across this barrier. Is it possible for energy to be transferred from the one on the left to the one on the right? Is it possible for a particle to be going fast over here and transfer energy and increase the overall energy over here? Yeah, technically it is, especially if you think about one particle. But we have tons and tons of particles, right? On the whole, it's orders of magnitude more likely that we're going to transfer energy from the right and to the left. Although it's possible to go from left to right maybe occasionally with one particle, it's virtually impossible. It's so incredibly improbable that all of the energy over here would transfer to the hotter object, because you would have to have the perfect alignment of all these different probabilities, right? And so when we're looking at the big picture at like an entire sample of gas, it always goes from hot to cold, because it's orders of magnitude more probable that it will do that. Now, all that just kind of helps you wrap your head around what entropy really is and how this energy transfer is really occurring. We're always going to be looking at the big picture. So at the macro level, it always goes from hot to cold because of the likelihood that we're going to have more fast particles striking from the hot side than on the cold side. All right, so there's 2 types of dispersal. One, matter, and then also energy. So inside the matter, there's 3 types of matter dispersal. We could have phase changes, which is what this is showing. When you go from a solid to a liquid, you're increasing the entropy because you're increasing the amount of dispersal or disorder, right? A solid is more orderly than a liquid. And a gas is less orderly than a liquid. So when you go from liquid to gas, you're also increasing the entropy. So that's a positive delta S. Also, when you go from solid to aqueous, you're increasing the entropy because those particles now can move around more freely. They're more disorganized. They're more random, however you want to think of it. You can also disperse matter through production stoichiometrically. So if you take one molecule and you separate it into 2 molecules, you're increasing the amount of dispersal, right? And so whenever you're producing more moles on the product side, that's going to be an increase in entropy. And finally, gas expansion. If you increase the volume of a gas in a piston, for example, you're giving those molecules more room to move around, and so they can disperse more, and so that would be a positive delta S. Finally, energy dispersal. We can disperse energy by increasing the temperature. Higher temperatures have a greater distribution of particle speed. If you go back to the simulation where I have the colored particles bouncing around, you can actually see the Maxwell-Boltzmann distribution at the bottom, and the higher temperature one is more dispersed. So really there's 4 ways to increase entropy. We can do phase changes. We can produce more molecules than we started with through stoichiometry, through some chemical reaction. We can expand a gas, or we can increase temperature. Those are ways that we can increase the entropy because we're increasing the amount of dispersal or disorder of either matter or energy. And that's really all you really need to know. We need to be able to identify whether a delta S is going to be positive or negative in a given situation. Don't hesitate to ask questions. Entropy is notoriously difficult to wrap your head around. If you have any questions right now, make sure you write those down, bring them up in class, and we can talk about it there. All right, this is Mr. Yergler, signing out.